So for this question, it basically asks us to verify the claim in this example right here, which is when we give a set X the discrete metric and E is any subset of X, and every element of E is an interior point of E, every point not contained in E is an exterior point of E, and then our boundary points. So basically there's three things we need to prove here. So let's recall some important definitions here. First one being if there exists a value of R greater than 0 that satisfies definition, then there's a valid ball, as well as for the discrete metric as well. As well for the interior exterior point definitions, and as well for the boundary point definition, which states that it is a boundary point if it is not a interior or exterior point. So basically, the main idea of how we want to prove this is, as you can clearly see here, the discrete metric is equal to 1 when x is not equal to y, and 0 when x is equal to y. So basically, if we have some r that is less than 1, right, let's just say, for example, 0.5, this represents a ball of just one element because this is just itself with that satisfies all values that is like less than 0.5, which is just 0. And so we just get this set of x naught, which since x of naught is in E, x naught is a subset of E. And thus all elements of all elements of x are, all elements of x that are in E are in the interior of E. So very symmetrical and very similar argument for part B. Since x naught is not in E, we can have the same ball argument right here, which is just itself. Since x of naught is not in E, this basically implies that the set of this union with E is equal to the empty set, and thus all x's that are not in E are in the exterior of E. And so for part C, we want to prove that the boundary points is equal to the empty set. And so for particular contradiction, let's just say that there exists, or that there is just some element that is in the set of the boundary points. And we know that if it is equal to the set of the boundary points, it's not in the set of the union of the interior of E and the exterior of E. Since the interior of E and exterior of E are equal to this, and it's union of these two sets where x is in E and x is not in E, this is basically implying that this set is equal to x, which basically means that x of naught is not in X, which is a contradiction.